I would like to thank the organizers for inviting me very much to be here. And, my objective in this talk is to show you there are infinitely many partial differential equations, usually nonlinear, that have the properties that we just saw, that have the Lax pairs, or virtually infinitely many conservation laws. And all these equations, they are related by the fact that generic solutions of these equations, they define metrics on open subset of the plane whose Gaussian curvature is -1. There is also a parallel theory for positive curvature, but during all these years working on this kind of theory, we find that the -1 is richer than the positive. Okay, I will start giving some sort of historical things, why -1 is important related to the differential equations, and then I'll give you some development of the theory up to the last year, let's say. So historically, the equation that was known to be related to surfaces with constant negative curvature was the sine-Gordon. And so Bohr in 1862, he showed that when you have a solution of the sine-Gordon equation, then you can define a surface locally defined in R3 whose curvature is -1 and vice versa. Okay, so then the geometry of -1 Gaussian curvature showed how to obtain a transformation between such a surface into another one, and this was done by Bäcklund. And then this geometric transformation was interpreted analytically in terms of what is now called Bäcklund transformation for the solutions of the equations. Then you start with a solution, and the Bäcklund transformation is an integrable system that provides you new solutions of the same equation. And so here is a picture of one solution given by, once you apply 0 to the transformation, analytic transformation, you obtain this solution, and once you apply 2 Bäcklund transformation, you get the solution on the right side. So solutions correspond to surfaces, and so the first solution corresponds to this surface, and the second one corresponds to the right-hand side surface, where the parameter of the transformation was chosen to be pi/2. Now, Bianchi showed a little later that there is this permittability property that once you start with a solution, with a surface or solution, doesn't matter, you go from one solution to another by a theta, like here is pi/2, from here to here pi/4, and then if you, after pi/2, you do pi/4, it's the same thing as starting with pi/4 and then getting pi/2. This is the Bianchi permittability property, geometric property, and it has its analytic interpretation that tells you that when you start with a solution, you impose Bäcklund, and Bäcklund with 2 parameters, and you have a new one here by this permittability property. And then you can go on doing this indefinitely. And the interesting part of it is that if you start with a solution, the first moment here, you have to integrate an integrable system, but then when you do the other steps, then they are completely algebraic. And this gives you a procedure to obtain infinitely many solutions of the equation. Now, in the 70s, there was a renewed interest in the sine-Gordon equation and also in other equations because they were applied to many physical properties, and also because they had those special solutions called soliton solutions. And so these solutions were observed by Scott in 1834, and these solutions have the property that they propagate without changing their shape, and even after they collide into other solutions of the same type, they keep their shape. And you can see this in the first example that I showed you on the right-hand side. this is two solutions colliding, and then they go on after the collision, keeping their shapes. Okay. So other equations that have soliton solutions are the KdV equation that we already had those lectures during the whole week about the KdV, and another one is nonlinear Schrödinger equation, which is found in fluids and nonlinear optics. And this is a complex equation here, but if you look at Q as being U plus IV, where U and V are real functions, then this Schrödinger equation can be repeated in this form. Okay. Now, I want to tell you about the differential equation that describes pseudo-spherical surfaces. Now, these surfaces, they have the characterization, the fact that a generic solution will define a metric in open subsets of the plane such that the Gaussian curvature is -1. Now, this is an intrinsic property. What I was showing before was surfaces in R3. Here, I'm mentioning about just Riemannian metrics on open subsets of the plane. The plane is X and T. And this is a concept that was, now we also, as I said before, we also extended this notion to differential equation to describe spherical surfaces. In this case, the curvature is 1. But from now on, I will go on just mentioning about the pseudo-spherical case that it seems to be richer, but there is a parallel theory. Okay? Now, this concept started in 1986. This was a joint paper with Chern, where we decided to introduce this definition. And this was inspired by Sasaki's observation that he mentioned that some differential equations, such as KdV, modified KdV and sine-Gordon, that could be solved by the AKNS, this is an inverse scattering method, that they represented metrics whose curvature was -1. So inspired by that, we decided to introduce this notion, and now we know that those differential equations, this set is much, much larger than what the AKNS class was doing at that time. Okay, so in this initial paper, besides giving this introduction, we also started with a systematic procedure of characterizing and classifying those equations. Now, so since the 80s, there have been a lot of papers in this direction of classifying the equations, and I will mention just some of the authors with Beals from Yale, Castro Silva, Cavalcante, Chern himself, Ding, Catalano, Gomez, etc. A lot of collaborators, or some of them former students. So I wanted to emphasize now the special properties of those equations. Now, why are they special first? This is a consequence of the geometric fact that if you have two Riemannian metrics with the same dimension and same constant sectional curvature, in case the dimension is bigger, then there is always a local isometry between those two metrics. So this means that in a sense, if you have two differential equations that describe the spherical surface, as I said, the generic solutions with defined metrics constant curvature, so theoretically there is a change of variables, of dependent and independent variables that should take a solution into the other. This is very theoretical, you know that they exist, but you cannot produce it. I mean, it's almost impossible. But this tells you that in the universe of so many partial differential equations, those are in a sense in an equivalence class. Okay, so now I will tell you this, the definition of the differential equation that describes pseudo-spherical surface is equivalent to saying that a generic solution, I'm saying generic because like sometimes 0 is a solution of the equation, but this will not give you any metric. But generic solutions will define a metric on open subsets of the plane, such that the Gaussian curvature is -1. And this is equivalent to saying that the differential equation is a compatibility condition of an SL2R linear problem. And this is sometimes called zero curvature representation. But for me, I prefer to look at -1 because -1, I know I am in a class of equivalent equation, let's say. Now, what is the importance of this linear problem? I will just go on, I'm just telling you why those equations are important, and later I will go into more details to show you how you define and how to apply the properties. Okay, so these equations, they may present properties such as Bäcklund transformation, superposition formula, infinite number of conservation laws, and they are natural candidates to being solved by the inverse scattering method. So they are, in a sense, considered integrable. I'm putting integrable into quotes because there is no definition of integrable equations, so we just mention the properties that are usually that they usually appear on those equations.
Could I ask a question?
Sure.
So, if you write the condition that the Gaussian curvature is 1, that is itself a partial differential equation.
Sure.
But yours is of different kind.
Yeah, yeah.
It will imply that the Gaussian curvature is 1, but it's not equivalent to it somehow?
I will get there, okay? I just want to mention why these are important, okay? So the Bäcklund transformation, as you saw in the case of the sine-Gordon, is because you can produce new solutions from given one. Superposition, you get no other solutions algebraically. And the inverse scattering method is because once you have an equation, you want to obtain the solution once you have u of x 0. You give us something for t equal to 0, and you want to get the solution for u of xt. And usually it may be done by using the inverse scattering method sometimes. And for that, we need a linear problem. And so these equations, they provide these linear problems. Also, I would, now this inverse scattering started with Gardner, Green, Kruskal, and Muir in 1967, but then it was reformulated as a Riemann-Hilbert problem by Beals and Koifman in the 80s. And now the geometry will provide you conservation laws for the PDE. And so I'm saying all these properties are related to the fact that the curvature is -1. Okay, now I give you a definition. When is a differential equation, differential equation for a real valued function u of xt describes pseudo-spherical surface. Now you need to find 6 functions Fij, which depend on u and its derivatives, such that when I define those forms, omega 1, omega 2, omega 3, the first 2 ones will define me the metric, and then the omega 3 usually is the connection form, and then you want this to satisfy the structure equations of -1 curvature. So this is the one that in principle gives you omega 3, the connection form, once you know omega 1, omega 2. And the last one is d omega 3 in general is minus k, which is Gaussian curvature, omega 1, omega 2. So in this case, I'm already saying that the curvature will be -1. So the difficulty in generating such equations or looking for them, I mean, is finding the functions Fij's. Okay, so just a simple example. Here is the sine-Gordon, u of x sine of u. So the omega 1 is given 1 over eta sine of u. Omega 2 is eta dx, 1 over eta cosine, and omega 3 u x dx. If you plug in those 3 omegas the way I saw, with the way I defined them here, you plug them in the structure equation, you get that the structure equations are satisfied if and only if u is a solution of the sine-Gordon. So the structure equations that I'm talking about, are exactly those 3 here. You plug in those omegas, And this will be satisfied if and only if U is a solution of the sine-Gordon. Another example is the modified KdV. I should mention that eta is a parameter. It has its importance in many different situations when you want to solve the AKNS eventually, or when you want to find infinitely many conservation laws. So I've just put two examples here. I could have done Korteveg de Vries, but the extent of these omegas are much bigger if you take KdV, but you can do it. I mean, so I just put those as an example for you to see how you can define the omegas in those two simple examples. And if you plug them inside those three equations, you will find that this is only satisfied if and only if, in this case, U is a solution of the modified KdV equation. Okay, now, as I told you, the differential equation should be also the integrability condition of a linear problem. So what is this linear problem in this case? Is given by this linear problem here for psi, and the matrix is AB. This is a 2 by 2. I mean, psi is a two-dimensional, two vector. Yeah? So it's A and B are matrices, and they are all defined in terms of the Fij's that I just gave you. So giving the Fij's or saying that I have a differential equation that describes the spherical surface is equivalent to saying that I have this linear problem. Now, the compatibility of this linear problem should be the differential equation. And the compatibility of the system is exactly this one here. Now, this is equivalent to the Lax pair. So when you look at this, you have the Lax pair for each equation, because the Fij's are written in terms of U and the derivatives of U. And then, although this is a 2 by 2 matrix, some of the terms, when you do this product here, are trivially satisfied, and the others will give you the essential Lax pair for the specific equation. So this, because A and B are operators, yeah, acting on U, because the Fij's are determined in terms of U and the derivatives of U. Okay, so this should be clear that once I give you the differential equations, I have the Fij's, and the Fij's give me also the Lax pair. Okay? All right, so one also can do in 3 by 3 equations, which is equivalent, but sometimes this could be a little bit easier. It just is equivalent. And you plug in the functions again to get the linear problem. Okay, so now if I go back to the examples that I just gave you, so U of xt was sine of U, I gave you the Fij's, and the last slide gave you how to define the matrices A and B that will give you the Lax pair. So just plug in this procedures that I just gave you here, the A and B, and then you will find the linear problem, which in this case of the sine-Gordon is exactly this. Okay, now I give you another, since we are in the Schrödinger Institute, I should give you the example that involves the nonlinear Schrödinger equation, which is this one up here. And you have the Fij's explicitly given, and if you write the linear problem, is exactly this one here. I mentioned you that there is a parameter eta, and it's for the definition, it's not important that there is a parameter. But for the application or looking for the conservation laws, the parameters are very important. Okay, so I should mention, as I said, there is a parallel theory with positive curvature. And in this case, if we change this minus ones into plus ones, we get the nonlinear Schrödinger plus that describe spherical surfaces. Okay, so again, the linear problems are determined by the Fij's. Okay, now I want to tell you how you get the conservation laws, and hopefully there are infinitely many once you have such an equation. So there are there is a geometric property that tells you whenever you have curvature -1, you can always change choose a special vector, two special vector fields, orthonormal, such that in one direction you have a geodesic, in the other direction you have an orocycle. Now, in order to do this, remember when we started with the equation, we had omega-1, omega-2. So the dual frame, the dual will be E1, E2. Now, in order to get the special frames of geodesics and orocycles, I have to make change with an angle, yeah, because it was orthonormal and now I have a new orthonormal. And this is an angle that is given by this system here. So once I have the equation, I have the Fij's, and if describes pseudo-spherical surface, that means that this system phi is integrable in the sense of Frobenius, so the mixed derivatives commute. So there exists such a phi, which is this angle, and moreover, this is a closed form. Once I have this phi satisfying this system, I plug in here, and this is a closed form. Now, assume that your Fij's are analytic in a parameter eta, let's say. Then the theory tells you that the phi will be analytic in this parameter, and then you can plug in here, and this will give you an analytic closed form in the parameter eta. So if you choose each exponent of this Taylor expansion of this parameter, then you will get infinitely many conservation laws. So this tells you how to get the infinite conservation laws for a specific equation. Later, I will give you even an explicit example of conservation laws for, I guess it's a system, if it's not equation. Okay. So this is how the geometry comes in. Initially, the idea was given in this initial paper, the Chern, but then later, in this other paper here, it's also almost an algorithm for how to get the conservation laws. Now, in practice, you don't need to solve the phi. What you do is write phi as, if it's analytic, then you write as expansion in Taylor series, and you go on and try to get those terms. You don't need to solve the system. So you get the coefficients of the expansion, Taylor expansion. Okay, so now I will tell you a little bit about the story of these classification theorems. So the first example, to try to attack the problem of finding all partial differential equations that describe the spherical surface, this is almost impossible. It's too big. And so what you do, you start imposing some conditions. And the first one that we did was imposing that F21 would be a parameter. And this is because we were inspired by this AKNS method there. But in those papers, the F11 and F31 could not depend on the parameter. But in our case, we let this condition free. And we started in the first paper obtaining classification theorems for evolution of equations of this type, U of t equal to f, etc., that describe pseudo-spherical surfaces with this assumption F21 is equal to eta, just this one. And then you get Burger's KdV, modified KdV, etc. In this paper, later we looked for this kind of equations, UTT equal to f and up to second order derivative of x. Still F21 is equal to eta. And Rabello in '89, this was a former student of mine, looked for equations of uxt equals to f. Now, among so many differential equations that he found in his thesis, he got this one here. U of xt equal to u plus u cubed second derivative of x. Nowadays, this equation is known as short pulse equation because in 2004, it appeared in nonlinear optics. So Schaefer and Wayne, they showed that this equation describes the propagation of ultra-short light pulses in silica optics, and so this is important for transmission of data. Since then, there are hundreds of papers on this equation. Okay, so, but it took about 20 years to find out that this equation describes the important physical phenomena. But as I said, in this classification theorems, we have many equations, infinitely many actually. And so it's interesting to find which ones would be applied to physics phenomena. Now, the short pulse was shown to be integrable in the sense of inverse scattering method. And this was done in this paper together with Beals and Rabello in the 89. And this is because in this class of equation, we have where G satisfies, G is a function of U that satisfies this here, and you have mu constant, alpha constant, beta constant, and this is a plus or minus 1. And by considering special constants, then you get the sine-Gordon equation, the singe-Gordon, the Liouville, and the short pulse equation. Now, not the whole class was proved to be integrable using the inverse scattering, just half of it, let's say one plus sign, not the minus 1. So this means that even if you have the linear problem, it doesn't mean that you can just plug in the machinery and solve it for the inverse scattering. Okay, so in 95, we got a complete characterization of this type of equations without any restrictions of phi j, but then this is a very technical and theoretical result. In 98, Reyes included the independent variables. Now, this theorem here, they can be used in two ways. One of them is check if a given differential equation describes a pseudo-spherical surface, or generate huge classes of differential equations that describe pseudo-sphericals with potential applications to engineering or physics. Okay, now Gomez in 2010, he studied this type of equation. Now he changed the initial, the way he included the parameters. He included 4 parameters actually. So he decided to use F21 as a linear combination of F11, the same with F31. And his classification gave him 4 theorems. I'm not going to give any classification theorem because they are very technical and it would be boring for a talk like that, but I will certainly pick up some equations in each of those classification theorems. So here we have differential equations involving arbitrary functions. So this is an infinite dimensional set of equations that describe pseudo-spherical surfaces. And the associated linear problems, now they have 2 parameters. Now these 2 parameters, it's interesting because you might find out that one of them is more interesting than the other one. So the fact that you have more parameters, it's interesting. Now, as I said, his classification involved arbitrary differential functions of a certain type. So if you pick them properly, those arbitrary functions, you get the Kaup's-Kupperschmidt equation, which is this one here, Savada-Kotera equation, this one that looks nice, 5th order KdV equation. So all these are special cases that you obtain that describe pseudo-spherical surfaces by choosing the arbitrary functions that you can do. You can choose them. Now, more recently, in 2014, with Catalano and Ferraioli, we studied these kind of 4th order, and we used the same condition that Gomez used, that F21 and F31 is a linear combination of F11. We again have 4 types, very large sets of equations, and they are infinitely many again because they include arbitrary functions. Examples, by choosing those arbitrary functions, you have in this case, the fourth order member of Burger's hierarchy, some other equations, these ones here. Here we have constants m1, m2, and 0. We call the modified Kuramoto-Sivashinsky because m0 should be non-zero, but the limiting case will provide you the Kuramoto-Sivashinsky equation. 2015, we got this kind of equations here. Again, very, very large families of equations. And here you can see an infinite dimensional set of equations because you have u of t minus u of xxt equal to a constant m1 psi plus m2 x derivative of this arbitrary function psi, where psi is a function of ux, non-zero. So when you choose the psi appropriately, you have a specific equation. And this is what we did if by choosing these arbitrary differential equations, we got this one, for example, here, where lambda m1 and m2 cannot vanish simultaneously. This is still an infinite set of equations. Psi is arbitrary. Now, if you choose lambda equal to 1, m1 equal to 2, m2 equal to 0, and psi this kind of function, then you get the de Gasperis-Procesi equation. So what I'm doing here is showing that how many infinitely many equations that describe pseudo-spherical surfaces that have linear problems, have Lax pairs, etc. Now, again, you can have, by choosing the arbitrary functions properly, we get this 3-parameter family of equations involving these 3 constants. Here, the equation even involves the exponential of u. So when lambda is equal to 1 and m1 equal to 0, it reduces the Camassa-Holm equation. And m2 apparently is related to the critical shallow water wave speed. And when m2 is equal to 0, this equation has the so-called P-con solution. Okay, so as a remark, as I said, the classification results are constructive in the sense that each equation or each family of equations that describes pseudo-spherical surfaces, you give the functions Fij explicitly. And also the linear problem associated, which will give you the Lax pair. Okay, in 2020, I'm getting closer to recent times. So in 2020, we had some classification results with Catalano and Castro Silva of this kind of equations. Again, we have large families of such equations. Particular cases will give you this here, which looks like, I mean, it has H of u and L of u arbitrary functions. It describes pseudo-spherical surfaces. Here we have this equation here, and this one generalizes the short pulse equation. When m is equal to 0, this is equivalent to the short pulse equation. And this, another example, this is the constant astigmatism equation that describes pseudo-spherical surface or spherical surface. I should mention that those sets of equations that describe pseudo-spherical surfaces and the one that describes spherical, they are not disjoint. They are not disjoint. They can have intersection, meaning that given an such equation that it's in the intersection, you can have Fij's such that the curvature is -1, and you can have different Fij's such that the curvature is 1. Certainly, the linear problem will be different because the Fij's are changed. Okay, now systems of equations. We started working with, but I was running too much, but I'm not. Okay, so systems of equations, they were studied initially with Ding. This was a postdoc that came from China. And this paper was published. I mean, I'm putting the date and also the journal attached to all the previous papers. So we started looking at first order systems like that. And here you already have an infinite number of systems because P is arbitrary differential function. And so you get this one, u of t equals to u to 2 times h arbitrary differential equation, describes pseudo-spherical. This is another equation. And then we went to the second order. So we went to the second order motivated by the following equations: the nonlinear Schrödinger that I just mentioned before. Then there is the Heisenberg ferromagnet model. The Schrödinger flow maps into S2. This is a system because it's an S2, although there are 3 functions, but because they are on the sphere, it reduces to 2 functions. The Schrödinger flow maps into hyperbolic space. So motivated by these equations, we started looking for systems like that, u of t, which u minus v of xx here, and v of t equal to uxx, and on the right side, linear in the first order derivative of u and v in terms of x. So this one, by classifying this system of equations, we obtained this one. So these are reduced to this kind of thing. So we have constants involved. Delta is plus or minus 1. So gamma and alpha, delta, delta is just beta. So when delta is equal to 1, you have pseudo-spherical. When delta is minus 1, you have spherical surface. And alpha, beta, gamma, and sigma are constants. Whenever sigma is positive, if gamma is 0, sigma should be 0. Now, particular cases of this system here, because this is a 4-parameter family of systems, particular cases will give you exactly those 4 equations that I just mentioned. So we were inspired by the existence of these equations. We ended up finding a 4-parameter system of equations that describe pseudo-spherical surface. So now recent results that appeared in JDE in 22, we started looking with Kellmer systems of this kind, u of xt equal to f, v xt equal to g, where f and g are functions of u, ux, v, and dx. Now these results also involved arbitrary differential functions, and particular cases of these functions provide the Kono-Ono coupled integrable dispersionless system, which is this one here. Explicit, okay, now this was, in this case here, the referee decided that we should include some explicit conservation laws. Because, I mean, in mathematics, we know there exists, you don't care about explicitly finding them. But the referee said we should find some explicit examples. So this is of the conservation laws. So as I said, in this case, the Fij's are given, there is a parameter. So the conservation laws are obtained by a closed form, which is analytic in a parameter. So once you choose the coefficients of this parameter, you find the conservation laws. And just to answer the referee's question, I mean, so we just plugged in explicitly some of them, you see? This is the first one, this is a closed form, this is the second one, and it goes on, and it goes higher in the degrees of the functions of u and v, okay? But it can be done. I mean, in the case of the Kono-Ono coupled system, also we obtained the conservation laws, infinitely many. And so these also, they look, I mean, it goes more and more complicated when you go down here on the higher degree of the closed form. All right. So I want to mention that now that we've done some things also on elliptic equations. We started going back to the Bäcklund transformation, it was geometry for surfaces in R3, and we looked now for surfaces in the Lorentzian three-dimensional space. And we started to sort of imitate the constructions, and we ended up finding that, in particular, the surfaces in L3 with Gaussian curvature -1 correspond to solutions of the elliptic sine-Gordon and elliptic singe-Gordon. And there was also, so we know that these equations describe several physical phenomena, and the geometric theory, again, sort of Bäcklund transformation and superposition formula. But in this case, it was very, very unusual. So what happened is that instead of, as the classical Bäcklund that provides solutions of the same equation, the Bäcklund transformation here starts with a solution, let's say, of the elliptic sine-Gordon and provides you a solution of the elliptic singe-Gordon and vice versa, which is sort of very different from the classical theory. And then you can obtain explicit solution of the equations by using those transformations. And there is a superposition formula also. But now this superposition formula is very strange because you start with an elliptic singe-Gordon, you integrate, you find solutions of the elliptic sine-Gordon. And then you apply again the Bäcklund and you find elliptic singe-Gordon and so on. So you have to use them twice in order to obtain solutions of the same equation. And similarly on this side, you start with the elliptic sine-Gordon, then elliptic singe-Gordon, sine-Gordon, singe-Gordon, and you go on with this scheme. But after the first integration step, the rest is algebraic. I should give you some explicit solutions here. You start with a zero solution, which doesn't mean anything, and of the elliptic singe-Gordon, and then you have applied two distinct parameters, you obtain solutions of the elliptic sine-Gordon, and then the superposition again gives you a solution of the elliptic singe-Gordon, and this is defined on the complement of two curves. Now, I'm not going into the details of that, but I should mention that this geometric theory was extended to higher dimensions. This was in the 80s, 90s, something like that. So, and many people are involved here, Ablovitz, Aminov, Barbosa, etc. And so when we started, remember it was sine-Gordon. Sine-Gordon is one equation for u of xt. But if you think of it, when you look at the metric, you can think of it cosine of u and sine of u. So actually it's not u, it's cosine and sine, it's a vector. And so you can go in higher dimensions, and then you have a vector, which gives you the first fundamental form in higher dimensions. And so you can sort of imitate what was done in the two-dimensional case. And then you will require that the submanifold has constant curvature K, different from the constant sectional curvature of the ambient space, A bar. And then you can get Bäcklund transformation. We were able to prove the inverse scattering method was, we provided solutions. This was with Beals and, Beals. And there was also an intrinsic version, because I started with sine-Gordon as a solution for surfaces in R3. And then I ended up sine-Gordon just intrinsic geometry. Here the same thing. The intrinsic version is just a vector, while here in the first case, as submanifolds, you need the first fundamental form and the second fundamental form. So this turns into a matrix. But for the intrinsic case, you just need a vector. And we got Bäcklund transformation, superposition formula, and the inverse scattering method was applied to those systems, showing that they are integrable even in n dimension. And okay, so I would like to thank you. This is not a flower, if you think of it. It's just a pseudo-spherical surface. In R3.